I want to integrate 2 cosec x cot x minus x squared x dx. So we just need to use the standard results to find these integrals. And if you look at the list, when we have cosec, this is k is just a constant, but in this question we don't have a constant, so we just have cosec x times cot x, and that integrates to minus cosec x. So that means here that we have 2 cosec x cot x. We simply get minus 2, because these two, is just there, so we still keep the 2. But then the part that we have cosec x cot x integrates to minus cosec x. And again, from standard results, we know that sec squared x integrates to tan x, so we simply get minus tan x plus c. And for part j, we have e to the x plus 1 over x minus cosec squared x. So again, e to the x always integrates to e to the x, and 1 over x always integrates to len modulus x, and minus cosec squared x. So it's important to, again, not mix up these, because we have, for example, cosec cot x, and we also have cosec squared x. So as you can see, they're different. So cosec squared x integrates to minus cot x, right? So in this case, since we have minus cosec squared x, it integrates to cot x, because cosec squared x integrates to minus cot x, but minus cosec squared x integrates to positive cot x. So we have cot x, and then the constant of integration. So we have cosec squared 3x, and this is the type of the integration that we want to integrate f of ax plus b, which means we have a function, and inside that function we also have a linear function. So a simpler example was part D, where we had cos of 1 minus 2x, because here the main function is cosine, but we also have this nested linear function inside of that. So now here the idea is that we when we have functions in this form, we can differentiate the linear function, and the reciprocal of the derivative becomes the coefficient of the basically of the final answer. So in this case, 3x differentiates to 3, so 1 over 3 becomes the coefficient of the final function that's going to be the answer. And then we integrate that function, the main function, as normal. So in this case, we have cosec squared 3x, which essentially cosec itself, cosec squared, integrates to minus cot. So in this case, it integrates to minus cot 3x plus c. This is one way of doing these integrals. There is another way by just purely using standard results, which I will show you in a few seconds. But yeah, that's one approach here. So we get minus a third cot 3x plus c. So another approach is when we use standard results, because in terms of standard results, cosec squared of kx, where k is a constant, is just equal to, so this integrates to minus 1 over k times cot kx plus c, which is exactly what we had in the previous question. So this exercise is just all about using these constants, really, and we can either just memorize these in this as a general form, or just think about them sort of logically when we see them. Now for the next question, we have sec 4x times tan 4x, and we just need to remember that by just in the standard results, if we have sec kx times tan kx dx, this integrates to 1 over k sec kx plus c. So in this case, using the standard results rather than using the approach that, which is essentially the same thing. So all I did in part E is exactly just using this standard result, but in a slightly non-memorizing way. Anyway, so here k is just 4, so this becomes 1 over 4, and then sec kx times tan kx is sec kx, which means sec 4x in this case, plus c. So first of all, for the exponential term that we have, e to the 5x, all we need to do is that in this case, because we have a linear function in the power, so we just differentiate that, and then the reciprocal of the derivative becomes a coefficient. So in this case, 5x differentiates to 5, so therefore we'll have 1 over 5, which is the reciprocal of that, times the function itself, which is e to the 5x. And you can always double check by differentiating this, and you should get e to the power of 5x. So in this case, if we differentiate, we'll get exactly the same thing. Now for the second term, which is 1 minus x to the power of 5, we use the reverse chain rule. So we can make an educated guess, and always we always raise the power by 1. So in this case, this is our educated guess, and then we just need to adjust this. So let's differentiate this and see how good this guess is. So by differentiating, we'll have 6 times minus 1 minus x to the power of 5, which is minus 6 1 minus x to the power of 5. And as you can see, 1 minus x to the power of 5 is common, but we don't want to have this minus 6 term, right? So I mean minus 6 as a coefficient. So what we do here is that we just include this multiplier of 1 minus 1 over 6, because if we have that, then that will cancel out with this minus 6 here, essentially, if we differentiate this function. So therefore, the derivative, when we integrate, we'll have minus 1 over 6, 1 minus x to the power of 6 plus c. Okay, so whenever we see a fraction that its numerator looks like the derivative of the denominator, then most of the times, if we integrate the fraction, then we'll get ln. So in this case, we can start with an educated guess that when we integrate, we'll get ln x. Now, let's now differentiate this and see how accurate it is. So when we differentiate, we'll get 1 over x. And remember that here we have 1 over kx. So basically, we just need to have this constant as well, 1 over k times 1 over x. So essentially, here must be 1 over k ln x, because if that's the case, then we'll get exactly 1 over kx. So therefore, when we integrate, we'll get 1 over k ln x. Now, we need to substitute the limits so that we can solve the equation and find the value of k. So first of all, I'm just going to take 1 over k out, and then we'll have ln of e to the 8, which is just positive, so we don't need to write down the modulus. Ln e to the 8 minus ln e squared is equal to 1 over 4. Okay, now let's simplify. So first I'm just going to multiply both sides by k, and then ln e to the power 8 is just 8, and then here is just ln e squared is just 2, and then we have k over 4 on the right hand side. So we can multiply both sides. First of all, here is just 6, both sides by 4, and we'll get 24 is equal to. So in part E, we have 3 over 1 minus 4x, and we want to integrate this. So whenever we see functions that, or actually fractions, that the numerator looks like the derivative of the denominator, then the very first thing that we can always check is checking log. So in this case, let's say if we integrate, we'll get ln 1 minus 4x. Now, this is the first step, just writing the ln of the denominator. The next step is that differentiating the guess, and then just adjusting the guess, basically. So in this case, if we differentiate, we'll get minus 4 over 1 minus 4x. Now let's compare that. So here, the denominator is exactly the same, which is a good sign. Only the number on the numerator here is 3, here is minus 4. So we just need to make some adjustments such that we'll get 3 here instead of minus 4. And that just means that if we multiply this by this fraction 3 over 4, then sorry, 3 minus 3 over 4, because the negatives should also cancel out, then we'll get exactly 3 over 1 minus 4x. So therefore here we should have this constant as well, minus 3 over 4 ln for ln 1 minus 4x plus c. Now for the next part, which is 3 over 1 minus 4x squared. Now here we should be careful, because the problem is that we can no longer use ln, because if you look at the denominator is a quadratic, but numerator is just a constant. And that simply means that the numerator isn't the derivative of the denominator, as opposed to the previous case that we had a linear function and then a constant. So always there should be just only one unit difference between the order of the highest x power. So in this case, the difference of the order is 2, so that's why I cannot be ln. But what we can do instead is that we can rewrite this as 3 times 1 minus 4x to the power of minus 2dx. Now, at this point, we just need to make an educated guess that, let's say, if we integrate, we'll get 1 minus 4x, and we always add 1 to the power. So in this case, basically, you just take this number that is, sorry, this expression on the denominator, but obviously the power becomes negative because it's on the numerator, and then you just add 1 to the power. So minus 2 plus 1 is minus 1. So let's say this is the function that we get after integration. Now again, we just need to adjust and just see if this is correct. So if we differentiate, we'll get minus 1 times minus 4 times 1 minus 4x to the power of minus 2. Now as you can see, this is equal to plus 4 over 1 minus 4x squared. So when we compare this, the denominator is exactly the same as here. Again, this constant of 4 here is something we don't want. We want to have 3. So we just need to multiply this by 3 over 4. So therefore, all we need to do is that we just need to have this 3 over 4, and that basically gives us the answer. Okay, first of all, let's rewrite this integral in a better form, basically. So 1 over sine squared 2x is the same as cosec squared 2x. Now let's not change this term, because this is the type that it's eventually integrates to ln. So it's just better to keep in this form. But this one is the reverse chain rule, so it's better to be written in this form. Okay, now cosec squared 2x. So first of all, we differentiate the linear function inside, which is 2, and then that as a reciprocal becomes a coefficient, which means a half. And then cosec squared itself, in general, cosec squared integrates to minus cot. So in this case, we'll have minus cot 2x. Now, for 1 over 1 plus 2x, as I said, because the numerator is sort of basically the derivative of the denominator, so this is the ln basically. So we can first make an educated guess that the integral, when we integrate, we'll get ln of 1 plus 2x. Now let's differentiate this and see how good is this guess. So if we differentiate, we'll have 2 over 1 plus 2x. So that means we need to have a 1 over 2 as a multiplier, because that 1 over 2 will cancel out with this 2, and therefore we'll get 1 over 1 plus 2x. So therefore this integrates to half ln 1 plus 2x. Now we sort of do the same thing with the last term, which is reverse chain rule. So our educated guess is 1 plus 2x to the power of minus 1. Now let's differentiate this. Again, for reverse chain rule, we just add 1 to the power. So its derivative is minus 1 times 2, and then 1 plus 2x to the power of minus 2. So essentially we have minus 2 1 plus 2x to the power of minus 2, and we just want to get rid of this minus 2. So we just need to have minus a half to get rid of this minus 2. So therefore, this will integrate to minus a half 2x plus 1 to the power of minus 1 and plus c. We have tan squared 3x and we want to integrate that. So this section is all about using trigonometric identities to sort of make complicated looking trigonometric expressions into some easier ones that we can basically integrate. So in this case, when we have tan squared 3x, we can use this identity that basically 1 plus tan squared x is sec squared x. So essentially, if you rearrange this and just make tan squared the subject, it will become tan squared x is equal to sec squared x minus 1. So here, the only thing which is different is that it's tan squared 3x, but it doesn't make a huge difference because all we need to do is that it just becomes sec squared 3x minus 1 dx. And now, the good news is that sec squared in general just integrates to tan. So in this case, since it's 3x, we just differentiate 3x, which is 3. So that comes out as a coefficient, which is 1 over 3. And then sec squared just integrates to tan. So it becomes 1 over 3 tan 3x. And then minus 1 is just integrates to minus x plus c. Now, part F, first of all, we just need to expand this, but it needs a similar trick. So we'll get cot squared x minus 2 cot x cosec x plus cosec squared x. Okay, so the identity that we need to remember is that basically, because we have the term cot squared x, and integrating that is not something we want, but instead, we can rewrite that as, because cot squared x is equal to cosec x squared minus 1, and then we can easily integrate cosec squared. So we can then rewrite this as cosec squared x minus 1, and then we also have this cosec squared here, and then this middle term, which is minus 2 cot x cosec x. Now this is in a form that all of these are just standard results. So first of all, here cosec squared x plus cosec squared x just makes 2 cosec squared x. So I'm just going to write 2 cosec squared x minus 1, and the rest doesn't change. Okay, so at this point, we just need to use the standard results, because cosec squared x simply integrates to minus cot x. So we'll get minus 2 cot x. Minus 1 integrates to minus x. And then cot x cosec x integrates to minus cosec x. But since here it's minus cot x cosec x, obviously those are minus 2. So it's just going to be the opposite, like it will be plus cosec x plus c. Cos 2x over 1 minus cos squared 2x. So first of all, 1 minus cos squared 2x is equal to sine squared x, right? That just comes from the basic identity that cos squared x plus sine squared x is equal to 1. Now in this case, we have cos squared 2x. Therefore, we'll have sine squared 2x. 2x here inside. So I guess it's better to use brackets here. Okay. Now, we can now rewrite the denominator as sine x times sine x dx. Sorry, it's 2x. So we have cos 2x sine 2x times sine 2x. Now, the interesting part is that we have cos 2x over sine 2x, which is basically cot 2x. And then we'll have 1 over sine 2x, which is basically cosec 2x. Okay, So now we have just cot 2x times cosec 2x. And if you remember, this is one of the standard results that in general, cot x cosec x integrates to minus cosec x. But here, since we have 2x, so we need to take that into consideration. So basically 2x differentiates to 2, and then the reciprocal of the derivative comes out, which is a half. So a half times minus cosec 2x plus c, which is basically the same as minus half cosec 2x plus c. We want to integrate 1 over sine squared x cos squared x. So whenever we see some trigonometric functions that are not standard results, then chances are we need to use trigonometric identities to rewrite them in nicer forms so we can use the standard results to integrate them, or maybe some other methods that we'll learn later on. So in this case, we have sine squared x times cos squared x. So normally when you have the product of sine x and cos x, then it's probably the double angle formula of sine that is going to be used to rewrite this in a nicer form. So recall that sine 2x is equal to 2 sine x times cos x. But in this case, we have sine squared 2x. So that means just the same expression, the right hand side is the same, but we also have that as squared. So which is equal to 4 sine squared x times cos squared x. Now here essentially we have sine squared x cos squared x, but we don't have this 4. So to count for that, what we do is that we can rewrite this as 4 over sine squared 2x. So if you just do this calculation, because remember that if you have 1 over 4 sine squared 2x, then this is essentially equivalent to this denominator. So if you then have 1 over 4, then you can rewrite this as 4 over sine squared 2x. So that's the reason. Okay, now we can simply integrate this because sine squared 2x can be written as cosec squared 2x. So we have pi over 6, pi over 3, and then 4 cosec squared 2x dx. Actually, I'm going to write 4 outside because it's a constant. And so this is now one of the standard results. So cosec squared integrates to minus cot. So in this case, we have 2x. So we also need to take that into consideration. So if you differentiate inside, it's just 2. So the reciprocal comes out, which is a half times minus cot 2x. And then we have the limits, pi over 3, pi over 6. Okay, so at this point, we just substitute the limits. So we have 4 times minus a half cot 2 pi over 3 minus, then the next time becomes positive, right? So it becomes positive because we have minus cot 2x. So we'll have plus half cot, basically 2 pi over 6. Okay. Yeah, so we just solve this, and at the end, we get 4 root 3 over 3. Okay, so first of all, we can rewrite cos to the power of 4x as cos squared x and then a squared. The reason is that we have an alternative form for cos squared x, so that's why I try to rewrite this in the form of cos squared x to the power of 2. And now we can substitute what we know for cos squared x, because again, remember that this is very useful. Cos squared x is equal to a half plus half cos 2x. So now we substitute a half plus, so, or actually we can just substitute the factor of that. So I mean the factorized version of that, so which is a half times 1 plus cos 2x squared. Okay, at this point we just need to square this. So we'll simply get in this case 1 over 4, and then inside the bracket we have 1 plus cos squared 2x plus 2 cos 2x. Okay. Now at this point, we can expand the bracket and multiply out 1 over 4, but we first need to rewrite this term also in an easier form, that it doesn't have a square. So it just, the same pattern as above, but in this case we have cos squared 2x. So what happens here is that cos squared 2x is essentially equal to, so it's basically again a half, but a half times cos 4x this time. So it's always this power is double of that. So in this case, we rewrite this as 1 over 4 times, so now we have 1 from before, but also we have essentially a half a half plus half cos 4x, and then the final term, that is 2 cos 2x. Okay, so we just need to expand this and we'll get 1 over let's actually simplify the brackets, which is 1 plus a half, which is 3 over 2. So 3 over 2 times 1 over 4 is 3 over 8. So we have 3 over 8 plus 1 over 8 cos 4x plus a half cos 2x. And that's exactly the form that we want to do. Now in part B, we just want to integrate cos to the power of 4x, but the whole point of doing this was to finally have this in an easier form so that we can substitute and use that basically in our integration. So we have the integral of cos to the power of 4x dx. However, this is equal to the integral of 3 over 8 plus 1 over 8 cos 4x plus a half cos 2x dx, which is a very simple integration. So the first term, which is just 3 over 8, is 3 over 8x. Then, so here we have 1 over 8. So inside of cos we have 4x, its derivative is 1 over 4, which comes out, and then cos integrates to sine. So we have sine 4x. Now same trick for the last term. So we have a half, and then inside is 2x. So the derivative is 2, and 1 over 2 comes out, and we again have sine 2x because cos integrates to sine. Okay, so we just simplify this. We have 3 over 8x plus 1 over 32 sine 4x plus 1 over 4 sine 2x plus c. Okay, so this exercise is about integrating by using the reverse chain rule, which is essentially about making an educated guess of the potential answer to the integral and then adjusting that basically. So one of the most common cases is when the numerator of a fraction looks like the derivative of a denominator. So in A, we have x over x squared plus 4. And obviously, if you differentiate x squared plus 4, you will get 2x. So as you can see, the numerator looks very similar because in numerator you have x, and then if you differentiate x squared plus 4, you will get 2x. So as you can see, they're very similar. So when they're similar, and we have again a fraction that the numerator looks like the derivative of the denominator, we can always start with the educated guess of ln of the denominator. So that's because if you differentiate this ln function, you will get 2x here and then x squared over x squared plus 4. So as you can see, differentiating this is going to give you 2x, but here we only have x, so we want to adjust this so that we'll get x over x squared plus 4. So that means we need to have this constant of a half, because this half cancels out with 1 over 2 with 2, and then therefore this is just x over x squared plus 4, which is the same as this fraction. So that simply means that here the educated guess that we made also needs a half. So that's the adjustment that I mentioned earlier. Okay, so at first it might be very hard, and maybe it may not seem very convincing, but once you practice, you can quickly solve these integrations. And these are actually one of the easiest integrations, as you can see. Now in part B, we have e to the power of 2x over e to the 2x plus 1. So again, it's the same idea because the numerator looks like the the derivative of the denominator. So the first guess is that this is equal to ln of the denominator, basically. Now let's differentiate this and see how correct it is. So when we differentiate, so we'll have a fraction, and then here the derivative is 2e to the power of 2x over e to the 2x plus 1. So again, as you can see, this is very similar to the fraction, but with this additional constant of 2. So again, we just need to multiply this by half to get rid of that 2. So therefore here must be half ln of e to the 2x plus 1 and then plus c. In this case, we have x over x squared plus 4 cubed. And essentially, whenever we see functions in the form that we basically have a bracket that has a power, that's normally the case that we basically make an educated guess that, because here the thing is, we have x over x squared plus 4x cubed, and the numerator sort of looks like a denominator, not exactly, but looks like the derivative of the denominator. So whenever we have that sort of function that we can kind of see a connection, then chances are it's reverse chain rule. And in this case, and in terms of reverse chain rule, there are mainly two main methods. So one is making the educated guess by having the natural log of the denominator, which is not going to work in this case, because if you take the natural log of this and then you differentiate that, so that's going to be x squared plus 4 and then cubed here. So then you'll have x squared plus 4 cubed, and then when you differentiate that, you're going to have 3 times 2x, and then you have x squared plus 4 squared and so on. As you can see, it's not going to give us this function. So the first case doesn't work, the natural case, the natural log. But the second case is when we basically look at the bracket, and then in this case, first let's rewrite the integral in the form x times x squared plus 4 to the power of minus 3 dx. Now in this case, we take this bracket and add 1 to the power, so we'll get x squared plus 4 to the power of minus 2. Now this is our educated guess. Now let's differentiate it and see how close this is to x over x squared plus 4 cubed. So when we differentiate, we get minus 2 times 2x and then x squared plus 4 to the power of minus 3, which is minus 4x over x squared plus 4 cubed. As you can see, this is very similar. The only thing that is missing is just, actually, we don't want to have this constant of minus 4. So to account for that, we can have a constant of minus 1 over 4 here, and that's basically the answer. So minus 1 over 4 x squared plus 4 to the power of minus 2 plus c, that's the answer to this integration. Because when we have minus 4 here, then that cancels out with this minus 4, so we'll have x over x squared plus 4 cubed. Now it's the same approach in part B, because again, when you use the natural log, this is not going to work, because essentially the order of the power is what basically kind of gives us a hint that natural log is not going to work here, because the order of power is 3, and then when you basically differentiate, you'll have also a power of 2, but here it's different. So again, we rewrite this as e to the 2x times e to the 2x plus 1 to the power of minus 3 dx. Now the guess is e to the 2x plus 1. We always add 1 to the power, so to the power of minus 2. Now let's differentiate this. We'll have minus 2 times 2e to the power of 2x and then e to the 2x plus 1 to the power of minus 3, which is minus 4e to the 2x and then e to the 2x plus 1 cubed. Again, as you can see, this is very similar. We just don't want to have this -4. So if we have -1/4, then these two are going to cancel out. So therefore, here -1/4 is missing. So this section is about integrating by using the reverse chain rule. So in this exponential case, we can first make an educated guess that let's say when we integrate, then we'll get something in the form e to the power of x squared. So this is our educated guess. But now let's differentiate this function and see how close the derivative is equal to here. And then based on that, we can make some adjustments to get exactly the same thing as here. So when we differentiate e to the x squared, we get basically the derivative of power comes down, which is 2x, and then the function itself, which is e to the x squared. So as you can see, this is very similar, but here we have 2, but here there is no constant of 2. So that means here must be 1/2. Because when we have 1/2, then essentially that 1/2 cancels out with this 2, and we'll be left with x times e to the x squared. So yeah, basically the answer is half e to the x squared plus c. Now for part h, again, whenever we have some brackets and there's something outside, one of the first things that we can do is that, especially when the bracket has a fairly high power, in this case it's to the power of 4, basically the first guess is very simple. It's just the bracket but with power plus 1. So in this case, this is our first guess. Now let's differentiate this and see how close this is to the actual answer. So when we differentiate, power comes down, and then the derivative of inside, so sine differentiates to cos. Since it's sine 2x, it differentiates to 2 cos 2x, and then we have the bracket, but with the power reduced by 1, which becomes 4. Now when you compare this to this function here inside integral, as you can see, we have the brackets are the same. We have cos squared 2x in both of them, but here we have 5 times 2, which is 10, so an additional constant of 10. And that simply means that we must have 1/10 to cancel out so that we get the same thing as above. So therefore, here there must be 1/10. We have sec squared x times tan squared x, and we want to integrate this. Okay, so this one is a bit less obvious in compared to the previous examples. So here we have sec squared times tan squared x, and when we look at this, there's actually not a very helpful way to use trigonometric identities. So the best way here is using the reverse chain rule, essentially. And here the trick is that to just remember something very, very important. And that is, if you have tan and you differentiate tan, then you will get sec squared x. So that's very important if you notice that. Because if you notice that, then you can write, like your first guess can be tan cubed, essentially. So I'm going to write in this form. So tan cubed, actually tan x cubed, which is the same as tan cube x, but this way is going to be more helpful for us now. So yeah, the reason that I wrote tan x cubed is because there is a relationship between tan and sec, right? So the way that it helps is that if we differentiate, obviously the power comes down, and then inside, which is tan x, it differentiates to sec squared x, and then we'll just then have tan x squared, like this. And that's exactly, almost exactly the same as what we have. We just need to have another constant of 1/3. So therefore here must be 1/3 tan x cubed. So yeah, as I said, this one was less obvious, but the point is that the integrations aren't always as straightforward as just taking something and just add 1 to the power. So in this case, we still did the same thing, but you could, ask that why didn't we just do sec cubed x? And that way, obviously, we are not going to be able to solve that. So yeah, it was very important to remember the connection between tan and sec squared x, which sec squared x is its derivative. Okay, so now part J, we have sec squared x times 1 plus tan squared x. Okay, first of all, let's expand the bracket. So we'll have sec squared x plus sec squared x tan squared x. Okay, so here is interesting because sec squared x essentially integrates to tan x, because sec squared x is the derivative of tan x. So this is just this part is simply a standard result. So it integrates to tan x. And then this part is what we just solved in part I. So sec squared tan squared x integrates to 1 over 3 tan cubed x plus c. The fact that we have a higher power, we have a bracket with a high power and then a bracket with a lower power outside. So in this case, the first educated guess is that the answer is basically x squared. So x squared plus 2x plus 3 to the power of 5. So now let's differentiate this and see how close we are. So when we differentiate, we get 2x plus 2, also times 5, and then we'll have the main bracket x squared plus 2x plus 3 to the power of 4. Okay, so this, as you can see, the big brackets are the same. Now here we have 2x plus 2, but here is x plus 1. So here we can actually factorize, right? If you take a factor of 2, then this will become essentially 5 times 2x plus 1, right? So now even x plus 1 is the same. We just have this 5 times 2 outside, which is 10. And so in order to sort of cancel that, we need to have 1 over 10. So therefore, here must be 1 over 10. And then the rest is just the main bracket to the power of 5. Okay, now for part B, we have cosec squared 2x times cot 2x. Now, in this case, we just need to remember the relationship between cot x and cosec x, because in general, whenever we have cot x, then cot x differentiates to minus cosec squared x. And that's very important in this question, because we can then make the educated guess that when we integrate, we'll get cot squared 2x. So now let's differentiate this, because when we differentiate, we'll have 2 times inside is cot 2x, so that essentially differentiates to minus 2 cosec squared 2x, and then the bracket but with power minus 1, which becomes just cot 2x. So when we compare this, we have cot 2x in both expressions, and then here we have cosec squared 2x, the same as here. We just have this minus 4 constant. So again, we need to have minus 1 over 4 outside to cancel out. So therefore, here we have minus 1 over 4 cot squared 2x plus. So first, we can start by expanding the brackets. And that gives us cos squared x minus cos x sin x plus sin x cos x minus sin squared x dx. Right, so the middle terms cancel out because minus cos x sin x plus sin x cos x is just equal to 0. So we get cos squared x minus sin squared x dx. Now remember that this is one of the identities that you can use, because I mean, one of the double angle formulas, not identity. So cos squared x minus sine squared x is simply equal to cos 2x. So that's very helpful because we can integrate this very easily. So we have the integral of cos 2x, and that is equal to, so a half times sine 2x. So we first basically write the reciprocal of this coefficient of x, and then we integrate cos, uh, which is just sine. And for the last part, we just need to substitute each of these values. So we'll first have, we can take a factor of half, and then sine 2 pi by 3 minus sine pi by 6. And the answer is equal to root 3 minus 1 over 4. Now, this is the type of integral that this can be thought of standard results if you have memorized that. Otherwise, we can just use trigonometric substitution to solve this. So in this case, we can use the substitution x is equal to tan u. Now that's because when we differentiate x, then with respect to u, we'll have dx by du is equal to sec squared u. So this is one of the standard results, that when you differentiate tan, you'll get sec squared u. Or actually, you can just do the differentiation manually by the quotient differentiation when you do the because tan u is equal to sine u over cos u, so you can just use the quotient rule. Anyway, so that differentiates to sec squared u, and that means dx is equal to sec squared u du. Now let's substitute this into the integral. So we'll have 1 over 1 plus x squared, which is tan squared u times dx, and dx is sec squared u du. But remember the identity 1 plus tan squared u, which is sec squared u, right? So we can now substitute that. That becomes 1 over sec squared u times sec squared u again, which is just integral of 1u, and that integrates to u plus c. And now, so x is equal to tan u. So when you do the inverse of both sides, you'll have arc tan x is equal to u. So that means this is equal to arc tan u, arc tan x plus c. Okay, so for the first step, we just need to draw the graph of f of x just to get an understanding of how it looks. So in terms of factorization, this is equal to x minus 2 times x plus 1, which means that the roots are positive 2 and negative 1. So therefore, a very quick sketch of this graph looks like this. So we have basically something like this, where here is minus 1 and here is positive 2. Okay, so now when we want to integrate the modulus of f of x, that's basically about sort of this region that is negative is also going to be positive, right? So that's what happens when we do the modulus, because you'll have a shape that will look like this. So if you ignore the green parts here, then the modulus part of that is going to look like this, because this side will just be reflected. That's just because it has to be positive. But I'm just going to keep this shape because it helps us in terms of writing the integration in simpler steps. So in order to consider the modulus, we need to have 3 separate integrals basically, because essentially we are first integrating from, remember that the furthest point here is -3, and then here is +3. So essentially at the beginning, we are integrating from -3 to -1. Um, so we have x squared minus x minus 2 dx. So this part is already positive, so the modulus has no effect, that's fine. And then the second integral is going to be for the part that the modulus will actually have impact, because that's from -1 to 2. But remember that we do negative, so we'll have, this is the first integral, then minus the second integral. And the reason that it's minus is because if you just integrate this region from -1 to 2, then this is going to give you a negative answer, because this is below the x-axis. So to account for the impact of the modulus, we have negative here, so that the answer is going to be positive. And finally, plus the final integral, which is from 2 to +3. And this way, we can basically integrate this. So obviously, we just need to integrate this once and then evaluate this for each part. So first of all, when we integrate, we'll get 1/3 x cubed minus a half x squared minus 2x, and then we just need to evaluate this for each part. So the first part is when the bounds are -1, -3. And the second part is going to be minus when the bounds are, so just writing the same thing when we integrate. So the bounds this time for the second integral are 2 and -1, and finally for the last one, show between 3 and 2. Right, so at this point, we just need to evaluate each of them, and the first integral gives us the value of 17/3. The second integral gives us 9/2, again, because we have this negative. Without the negative, it would be minus 9/2. And then the third integral is 29/6. Right, so we just add all of these, and the answer is equal to 15. So, we should start by just factorizing and finding the roots of this quadratic so that we can draw the graph of that. So we'll have x minus 2 times x plus 1 is equal to 0, where x is equal to 2, or x is equal to -1. So a quick sketch, actually, I did that in the previous video. So is this, because the roots are -1, -1 and +2, and then we draw this from -3 to +3. Now, the interesting part here is that we want to integrate f of modulus x. So let's rewrite this quadratic, and we write this as modulus x squared for the first term, and then minus modulus x and -2. Now here, we should be careful, because this part, which is modulus x and then a squared, is basically the same as having just x squared, right? Because the modulus doesn't do anything here, because x squared is always positive anyway, right? So we can just write this as x squared. So these two are equal. However, the second term has to be minus mod x minus 2 is equal to. So the powerful thing to remember is about even functions, because that's the key to solving this question. Because a function is called even if g of x is equal to g of minus x. And now when you look at this function, and if you just apply this fact, then it's essentially going to be an even function. Because in this case, if we, let's say, substitute minus x into here, then we'll get x squared minus x minus 2, which is the same as if we just substitute x. We'll also get x squared minus x minus 2. So if you substitute x into f of x, we'll get this. And also if you substitute minus x into here, then we'll also get x squared minus x minus 2. So therefore, this is an even function. Now, the reason that we needed to know that is because there is a very powerful technique in terms of integrating even functions, is that when we have a bound that is symmetric, because even functions are symmetric. So in this case, when we are integrating this from -3 to 3, we can actually just write this as from 0 to +3 and then drop the modulus, because here the value of x is going to be positive, right? So we don't need modulus for that. And this allows us to integrate this as usual. So we just now integrate this as, so x squared integrates to 1 over 3x cubed um, minus x squared over 2 and then minus 2x. Now we just substitute 3 and 0. And actually, I just forgot to mention that we always double that value. So when we have an even function, and since even functions are symmetric, so we can just rewrite this as 2 times integral of 3 over from 0 to 3. And the reason is because if you just, if I show you a quick sketch, I think that's going to be helpful. So if you draw this graph, it's going to roughly look like this. And it's not the best graph here, but the idea is that this side is symmetrical to this side. So instead of integrating from the -3 to 3, which is the whole region, since it's symmetric, we can only integrate from 0 to 3 and then double that value. So that's what exactly we are doing. And so I forgot to write this 2 times at the beginning. Yeah, so now we just evaluate, and then the final answer, once we have substituted 3 and then take away 0 substituted, is going to be simply equal to -3. So in part A, we want to integrate x times 1 plus x dx. Now this section is all about integrating by substitution. So if you look at this integral, and the first thing might be that why can't just we write 1 plus x in the form x to the power of half and then expand the bracket and then continue as normal. But there's a big problem with that, because here the power is a fraction. So we cannot really expand this in the normal way that we do when the power is just a whole number. So that's why we cannot use the expansion here. And then the other method might be the reverse chain rule, but that one is not going to work either, because the problem is that the power of the bracket is not higher than this, because if we say, okay, let's say the answer is 1 plus x to the power of 3 over 2, then the problem is that when we differentiate, then we'll have 3 over 2 and then 1 plus x to the power of half. So we cannot get this x term. That's the problem. So instead of using all of these methods, in this case, we need to use the use substitution method. And this is, in fact, one of the most, if not the most powerful integration techniques. So this is something that you will be either given the substitution in the exam and you just use the substitution to integrate, or maybe more often you will not be given the substitution and you need to figure that out yourself, which you will be eventually able to do that by practice. So in this case, we are given that use this substitution to integrate. Okay, so for the first step, we just substitute, whenever we see 1 plus x, we substitute u. So also remember that the substitution is u is equal to 1 plus x. So instead of this term with a square root, we simply write square root of u, because 1 plus x is equal to u. But what about x? So it's actually very simple, because if we rearrange x and make x a subject, then we'll get x is equal to u minus 1. So here we'll simply have u minus 1. And also, what about here? Do we write dx? Because here the variable is now u, so we can no longer write dx. So what do we do instead? So what we do is that it's not that we cannot just write du like this, because we need to do something else. We need to take the substitution into account. So what we do is that we just take the substitution here, so u is equal to 1 plus x, and we differentiate that with respect to x. So in this case, the derivative is simply equal to 1. Now we rearrange this and make the x the subject. So we'll have dx is equal to du. Now in this specific example, so we simply just, because dx is equal to du, that means we simply write du here. But there are many cases that we'll get some additional terms that, let's say it might be u times du, which you will see later, so I don't want to confuse you. Okay, so this is the setup. Now the difference, the main difference of u substitution with other methods is that you have the first method is basically like the setup. It's not the integration part. So now that the setup is almost done, we can now integrate this. So first, let's rewrite root u in the form u to the power half. And now we are ready. So we just expand the bracket. We'll get u to the power of 3 over 2 minus u to the power of half du. And now we just add 1 to the power. So 1 plus 3 over 2 is 5 over 2. So we divide by that, which becomes essentially 2 over 5 u to the power of 5 over 2. And then here we add 1, which becomes 3 over 2. But we divide by that, which becomes minus 2 over 3 u to the power of 3 over 2 plus c. Okay, we are almost done, but just remember that at the end we need to substitute back and make this in terms of x. So u is equal to 1 plus x, so we just substitute that into u. So we'll have 2 over 5 times 1 plus x to the power of 5 over 2 minus 2 over 3 times 1 plus x to the power of 3 over 2 plus c. So in part 2, we want to integrate sine cube x. And so this section is about the method called u substitution, or just integrating with substitution. And in this question, essentially, we need to use this substitution u is equal to cos x. We can start by differentiating, because we always differentiate u with respect to x. So we have du by dx is equal to cos x differentiates to minus sine x. Okay, later this is going to be substituted into the integral. But before that, also, if you look at sine cube x, we need to find a way to rewrite this in terms of u, basically. Now, one possible way is to take a factor of sine, and then you'll have sine squared x dx inside. And now inside, which is sine squared x, you can use the identity that says sine squared x plus cos squared x is equal to 1, which means sine squared x is basically 1 minus cos squared x. And this allows us to substitute u into here, which is cos squared x, because u is equal to cos x. So here it becomes 1 minus u squared. And instead of dx, let's also substitute what we derived here. So we have du over dx is equal to minus sine x. And essentially, if we rearrange this, we'll have dx is equal to minus du over sine x. Okay, now we can substitute that into the integral as well. So we'll have minus du over sine x. So essentially, this minus will be simplified in the next step. So now we have sine and then minus sine, so they cancel out. So this with this, and then we'll be left with, so we have this minus, don't forget that. So this minus actually belongs to here, the denominator. So if you write like this, I think it's clearer. And then we'll have then minus basically the bracket, then 1 minus u squared, which means that we'll get u squared minus 1 du. And now this is a very simple integration. So this is equal to 1 over 3 u cubed minus u plus c. But remember that at the end we need to substitute back. So in this case, u is equal to cos x. So now we want to have everything in terms of x again. So we is equal to 1 over 3 cos cubed x minus cos x plus c. We want to integrate sec x times tan x root sec x plus 2. and we want to use the substitution u is equal to sec x. Okay, first of all, we differentiate u with respect to x, and sec x differentiates to sec x times tan x. Now we rearrange this and make the x the subject, so we have du over sec x tan x. Also, we need to find the value of u for the given bounds, basically. So we want to transform them. So u is equal to, so when x is equal to pi over 3, then u is simply equal to 2. And then when x is equal to 0, u is simply equal to 1. So now we have everything to substitute. So the upper bound is 2, lower bound is 1. Sec x, so instead of sec x, we just write u. And then we have tan x, so let's write that. And on the square root, actually, let's not write the square root. Let's simply use the form u plus 2 to the power half. And finally, instead of dx, we write du by sec x times tan x. Okay, so now we have everything to solve this integral. So first of all, note that we have tan x here, and that cancels out with this tan x. So on the other hand, we have sec x here, but that actually simplifies to u. I mean, sec x is u according to the substitution. So that also cancels out with this u as well. So we'll simply be left with u plus 2 to the power half du. That's all we have now. Okay, so this is simply a reverse chain rule integration. So let's make the guess u plus 2 to the power of 3 over 2. And now let's differentiate this and see if we need to adjust the guess. So we have 3 over 2 u plus 2. So if when we differentiate, the power comes down and inside just differentiates to 1. And then the power is 3 over 2 minus 1, which is a half. Now, this 3 over 2 times u plus 2 to the power of half is almost the same as here, but this coefficient of 3 over 2 is extra, so we want to have 2 over 3 so that they cancel out. Therefore, here there must be 2 over 3 u plus 2 to the power of 3 over 2. Okay, and finally, we just substitute the limits, and the final answer is 16 over 3 minus. And we want to integrate this. So this exercise is about use substitution, and in this case, we can't use other methods such as reverse chain rule or just some standard results. So substitution is a very suitable method here, and always just check the easier methods such as, or maybe the quicker methods such as reverse chain rule, standard results. So if they don't work, then you can think of other methods such as substitution. So in this case, as we said, we are going to take whatever is under the square root equal to u. At least that's a good starting point. It's not a guarantee that it's going to work all the time, but that's a good starting point. So let's say u is equal to x squared plus 4. So we differentiate this. We have 2x. Let's make the x the subject. So du over 2x. Now let's substitute this into the integral. So we have root u over x times du over 2x, and this is equal to, so u to the power half, and then 2x squared du. So here the interesting thing is that if you just rearrange this, then x squared is equal to u minus 4. So we'll have u to the power half over 2u times minus 2u minus 8. And let's simplify this. So we can take a factor of half out, and then it's u to the power half and u minus 4 here to u. So there is a problem here because we can't solve this integration in the current form. But what we can do is use another substitution here. So you just need to be careful because uh, at the end, we need to then substitute everything back and make this in terms of x. But other than that, this is also another common technique that sometimes you might need maybe two substitutions or maybe three substitutions, but three is a bit too much. So in the examples you'll see, you probably need maximum two substitutions in the worst case. So we can then make an additional substitution of saying that, okay, let uh, basically u equal to t squared. So now we do du dt, which is 2t, and du is equal to 2t dt. So let's substitute this back. We have a half, and then u to the power of half. This is just t, and then on denominator we have 2 squared minus 4, and then here is 2t dt. So we get a half 2t squared t squared minus 4 dt. So this cancels out, and then we'll have just t squared over t minus 4 times t plus 4 dt. Now this is at this point we just need to use partial fractions, and by doing so we'll get 1 plus 1 over actually here is t minus 2t plus 2. So t minus 2t plus 2. Yeah, so we'll have 1 over t minus 2 minus 1 over t plus 2 after using partial fractions. And now we can finally integrate this easily. So this integrates to just t plus 1 over, and here is ln t minus 2 minus ln t plus 2 plus c. And now just be aware that we need to make the substitutions back because t essentially is root u. So before that, let's rewrite this as t plus ln of t minus 2 over t plus 2 plus c. And now remember that t is equal to root u. So we have root u plus ln of root u minus 2 over root u plus 2 plus c. And finally, make the final substitution of u is equal to x squared plus 4. So root of x squared plus 4 plus ln of x squared plus 4 minus 2 ln of x squared plus 4 plus 2, and finally plus c. We have e to the 4x over e to the x minus 2, and we want to integrate this. And we're given the substitution u squared is equal to e to the power of x minus 2. So here we must be careful because the final form of the answer has to be in the form a over b plus c ln d. And this is a very common formats that you'll see in your exam, that they ask you to derive this so that it's in the same form as they are asking. So we first differentiate this. So for u squared, we use the implicit differentiation because the dependent variable has power of 2. So we get 2u du by dx is equal to e to the x. Now we make dx the subject, so that gives us 2u du over e to the x. And we also need to transform the limits. So first of all, when we have, so u squared is equal to, when x is equal to ln 4, that's just essentially 4 minus 2, which is equal to 2. And But we also need to be careful because this is u squared, so we take the square root and that gives us root 2 in this case. Also, for the next part, so when x is equal to ln 3, we just get 1. Right, now we have everything. So in terms of substitution, we have root 2, 1, and for e to the power of 4x, in terms of our substitution, we can actually use this part, because if we rewrite this in the form u squared minus 2 is equal to e to the x, and then if we raise both sides to the power of 2, then we'll get e to the 4x, right? So that means u squared minus 2 to the power of 4 is e to the 4x, and then for e to the x minus 2, that just again this expression rearranged. Actually, sorry, not rearranged, but it's just the same as u squared essentially. And also for dx, we substitute 2u du, and then for the e to the x part, we just need to again rearrange this once again, and we'll get u squared plus 2 in this time. And also just to correct this, when we rearrange this, we have u squared minus 2, which is equal to e to the x. So here is also u squared plus 2, not minus 2. Okay, now we can simplify some of this. So we have u squared plus 2, so that simplifies with this power, and the power becomes 3. And then this u simplifies with this u. And we'll have root 2, 1, then 2u squared plus 2 cubed over u du. And now this is the part that we just need to expand the bracket, and then basically just simplify this. So this is just some algebra really. So yeah, once we do all of the steps here, so we'll get 2u to the power of 5 plus 12u cubed plus 24u plus 16 over u du. And now we just integrate each of these. So first we have 1 over 3 u to the power of 6, then 3u squared, and 12u squared. So here is 16 ln u, because it's 16 over u, so u doesn't have the power of u is 1. Right, so now we just substitute this, basically the first the higher limit and then the lower limit later, and then we just simplify. So in this case, we have 1 over 3, and then root 2 to the power of 6 is 8, and then 3 times root 2 squared is just 6. 12 times root 2 squared is 24, and we have 16 ln of root 2. Okay, then we subtract when we substitute 1, which is 1 over 3 plus 3 plus 12 plus ln 1, but that's just equal to 0. So 16 ln 1 is just 0. Just realize that here actually is 3u to the power of 4, and so that means we need to change some of these. Basically for this part, that we have 3 times root 2 to the power of 4, that's essentially 3 times 4, so which is 20, sorry, it's 12. So we get 12 here, and now we need to just basically simplify this. Right, so once we simplify this, for top we have basically 8 over 3 plus 36 plus 16 ln root 2, and here is just 40, and actually I think here no, the bottom doesn't change. So yeah, we have 46 over 3 here, and now we'll get 70 over 3 plus 8 root 2. So A is 70, B is 3, C is equal to 8, and D is equal to 2. So which satisfies the form that they. And we want to integrate this by using the substitution. U squared is equal to 4x plus 1. Now, the interesting thing here is that it's actually a key lesson that it's not always this that we take u equal to something. Sometimes it can be u squared equal to something as our substitution, or maybe root u. So in this case, we are recommended to use the substitution. Actually, yeah, but when they say or otherwise, that means we can use something else if we want to. So, as usual, we start by differentiating. So remember, this is implicit differentiation because the dependent variable has power. So it becomes 2u du dx is equal to 4 because we are differentiating with respect to x. Okay, so we can rearrange this and make the x the subject. So that becomes u du over 2. And also, as usual, we transform the limit. So when x is equal to 20, we get u squared is equal to 81. So that means u is equal to 9. And when x squared, let me correct this. So when x is equal to 6, then u is equal to 5. Now, so we substitute this, and u is, so the limits are 9, 5. And then on numerator, we have essentially 8x, so we can rearrange this, right? Because u squared minus 1 over 4 is equal to x. So we'll have 8 times u squared minus 1 over 4 over. So on denominator, we just have root u squared, which is just u. And then for dx, we substitute u du over 2. Okay. So now it's all about simplifying the ones that we can. So essentially all of these simplify. So this 8 with 4 and with this 2, they all simplify. So that's nice. Then we'll have u squared minus 1 over, actually we have, this also simplifies because we have u and u here. So we just get u squared minus 1 du. And that is equal to u cubed over 3. So it's integral minus u 95. And finally it's 592 over 3. We have sine 2 theta over 1 plus cos theta. And we want to use substitution to integrate this. Okay, first of all, we need to decide what should be the substitution. And in this case that we don't have a square root or something that looks immediately inconvenient, we can take the entire denominator equal to u. That's just because the term on the expression in the denominator looks a bit messy. So because normally we like to set the parts that are more challenging or just messier equal to u. So we can start with u is equal to 1 plus cos theta. Du by d theta is equal to minus sine theta. And then rearranging this to make d theta the subject, we get du over minus sine theta. Also, let's transform the limits. So when theta is equal to pi over 2, then u is simply equal to 1. And when theta is equal to 0, then u is equal to 2. Okay, now let's substitute this into the integral. So we have 1 and 2, and that just because we have basically for the upper limit we got 1 and for the lower limit we got 2. So that's why in substitution it looks like this. And So also for sine theta, let's just use the identity and rewrite sine through theta as 2 sine theta cos theta, because that's going to be useful when we want to simplify. So 1 plus cos theta is basically u, and now we substitute the u over minus sine theta into the theta, and now you can see the benefit of having sine 2 theta written as 2 sine theta cos x, because sine theta here cancels out with this sine theta, and we get, so we have 1 2, and we have minus 2 sine minus 2 cos theta over u du. And at this point, so we just need to substitute u minus 1 into cos theta, so we'll get minus 2 u minus basically minus 2u plus 2 over u du, and this is a very simple integration. So we have we can split this into two fractions, so we have minus 2 plus 2u, or actually 2 over u du, and finally we have minus 2u plus 2 ln u 1 2, and yeah, so we just basically substitute, and finally we get 2 minus 2 ln 2. We want to use the substitution u is equal to cos x to show that this is equal to 47 over 480. Okay, so as usual, we start by differentiating the substitution. So du by dx is equal to minus sine x, and we make dx the subject, so we have du over minus sine x. We need to transform the limits as well. So when x is equal to pi over 3, then so cos pi over 3 is equal to a half, and when x is equal to 0, this is equal to 1. So now we can substitute this. So remember that pi over 3, when you substitute that u is a half, and now when you substitute 0, you get 1. So you want to make sure that you substitute at the right place, even though that we have a half here and then 1 bottom. So now sine cube x, so let's rewrite that as sine times, so remember that if you have sine squared x, then that's the same as 1 minus cos squared x. So now sine cube x can be written as sine x times sine squared x, and we can then substitute 1 minus cos squared x into sine squared x. So here we have sine x times 1 minus cos squared x times another cos squared x dx. Now remember that u is equal to cos x, so let's substitute that here. We have a half 1 sine x, so 1 minus u squared times u squared, and for dx we substitute du over minus sine x. Okay, so now we have some simplification. So basically sine x cancels out with this sine x, and we'll have a negative, and so let's expand the bracket. So we are going to get minus u squared plus u to the power of 4 du. Okay, now this is a very simple integration. So we get minus 1 over 3 u cubed plus 1 over 5 u to the power of 5. And now we substitute the limits. And after substitution, we'll get 47 over 480. We need to use a very interesting trick, because obviously we can solve this by integration by parts, because I mean the first choice might be use substitution. So we can say let u be equal to ln x, so then this becomes u squared. So that's what we want to integrate essentially. And then so here du dx is 1 over x, and now we can just rearrange this. So this gives us dx is equal to x du, and now if we substitute into the interval, then we'll have x du. And so at the beginning we said u is equal to ln x, so if we just basically uh, raise both sides to the exponential function, which will become a to the power of u is equal to x. So here we can have u squared times e to the u du, which is just another integration by parts actually. So we started with u substitution, and then this leads to integration by parts. And then we can just use integration by parts to solve this, and at the end we just need to substitute everything back and have it in terms of x. So that's one approach. But since this exercise is about use of integration by parts, so I'm going to solve this with integration by parts from the beginning. And because it has a very nice trick that is very useful, and that is when we have just ln x and we don't have other functions, so we can write this as 1 times ln x squared dx. And now this allows us to take u equal to ln x squared and then dv dx equal to 1. So that's the trick that I was mentioning, that whenever you just have ln x or ln x squared, that's the trick you use. So you just rewrite that as 1 times that, and then you take 1 equal to dv dx. So u is equal to ln x squared, and dv dx is 1. We also want to find b. So du dx, that's the first thing that we want to do. And this is just chain rule, right? So when we differentiate this, we'll get 2 ln x, and then the derivative of inside is just 1 over x. So we get 2 ln x over x, and then here 1 simply integrates to x. Okay, so we use the formula of integration by parts, uv minus the integral of du dx times v dx. And now, so uv is just x ln x squared minus, inside we have du dx, which is 2 ln over x, times v, which is x. So just this times v will cancel out, so the x and 1 over x will cancel out, so we'll only have 2 ln x dx. Now here the problem is that we can't again integrate this directly, but what we can do is that we can use another integration by parts inside this, because similar to what we had, again we take u equal to ln x, and then dv dx equal to 2, so we find v. And this is a very common technique that at times you will need to use integration by parts twice or even sometimes more. But normally the types of questions you'll get often need you to use once or maybe sometimes twice. So du dx is equal to 1 over x, and then when we integrate 2, we'll simply get 2x. So now here you just need to be careful that you have this from the previous part, so x times ln x squared, this term is there, and then also this negative. Now inside this we substitute the new functions for the second integration by parts. So for the second integration by parts, we have u times v, which is ln x times 2x, and that is 2x ln x basically. And then minus, inside the integral we have 1 over x times 2x, which is just 2, right? So 2 dx. And yeah, so now that we have this simple integration, then we can just solve that. So we have x ln x squared minus, so minus 2x ln x, and then 2 integrates to 2x, so we have minus 2, so it is minus 2x, but another minus, that makes that positive 2x plus c. So this section is about integration by parts, and we use integration by parts whenever we have a product of two functions. Now in this case we have x and e to the x. So we normally start by taking the easier function equal to u, because we need to make two choices. So u and dv dx. So as you can see, we have four components, but only we make two choices, because if we know u, then we can find the u dx, and if we know dv dx, we can also find v. So the reason we need to make these choices is because of the formula of the integration by parts, which is essentially, once we have made the choices, then we can substitute into the formula and then integrate as usual. So the formula is u times v minus the integral of v times du dx dx. So essentially, here, so let's take u to be equal to x, and dv dx is e to the x. So we differentiate x with respect to, we differentiate u with respect to x, and that gives us just 1. So, and now we need to integrate e to the x to find v, but that's also equal to e to the x, right? So now we have all the four components. We just substitute into the formula. So again, formula is uv minus the integral of v times du dx dx. Now u is x, v is e to the x, so we get this, and inside we have v, which is e to the x, times du by dx, which is just 1. So that's the whole point of taking u equal to something easy, so that its derivative is also easy. I mean, maybe there might be some cases that u itself is not easy, it's not an easy function, but when you differentiate that, then the answer is easy. So we actually care about the derivative more than what the u is. And same thing applies here, because we want to take dv by dx, something that when we integrate that, which is e to the x, and that's going to be substituted inside the integral, then that can also be integrated easily. So now we just have the integral of e to the x, which is just e to the x. Okay, so this is integration by parts, and we have basically the product of two different functions. So we need to make two choices at the beginning, one for u, and the second one is for dv by dx. So as usual, whenever we have a trigonometric and an algebraic function, the priority is with algebraic function when we want to choose the value of u. But obviously, even if you, let's say, choose sine 2x to be equal to u, then once you continue your calculation in here, then you'll see that normally the integration is going to be very complicated. So I always suggest you that whenever you see that the integration is very complicated, make sure to switch the rules of what basically you chose for u. So you will see that if that's because of your choice, or maybe just the question that is complicated. So in this case, u is equal to 2x squared, so its derivative is 4x, and then dv by dx is sine 2x. So when we integrate sine 2x, we'll get minus a half cos 2x. Now we use the formula of integration by parts, uv minus the integral of du by dx times v dx. So uv in this case is 2x squared times minus a half cos 2x, which is minus x squared cos 2x minus, now du by dx is 4x, and 4x times v is minus 2x cos 2x dx. Now we can rewrite this as, so this negative sign comes out of the integral, or actually maybe, yeah, let's just do the negative for now, so it becomes plus 2x cos 2x dx. Okay, so the same as the last few questions, we need to use integration by parts twice, because now we have 2x times cos 2x, and again we need to use one more round of integration by parts. So we need to make the choices again. So u is equal to 2x, and that differentiates to 2. dv by dx is cos 2x, and that integrates to a half sine 2x. Now, we are going to substitute everything. So remember that we have this minus x squared cos 2x, and then for the second integral, basically, we now substitute the formula of integration by parts first, and then we then substitute each of these components into the formula. So it's basically du by dx times v dx. Okay, so minus x squared cos 2x plus u times v now is x sine 2x, and minus, so du dx is simply 2 d by dx, and then that times v is just sine 2x dx. Okay, so we have minus x squared cos 2x plus x sine 2x, and sine 2x integrates to minus half cos 2x, so we also have this negative, so it's positive half cos 2x plus c. Okay, so this is v integration by parts, and that's because we have a product of two different functions. So we have sine x times ln sec x, and now the question is which function should be chosen as u, but the answer is actually obvious, because whenever we have ln and a trigonometric function, the priority is with the basically ln, or just any logarithmic function. So u is equal to ln sec x, and we want to find du by dx, and then dv by dx is therefore equal to sine x. Now sine x simply integrates to minus cos x. Now you might be wondering, how can we differentiate ln sec x? So obviously we can use the chain rule, but actually this is just one of the results that you can also use, because essentially ln sec x differentiates to tan x. So yeah, that's something that we just need to be careful. But again, we can also go and just differentiate this by using basically reverse chain. Now also, this is the standard result that you'll have in your formula booklet, that the integral of tan x is ln mod sec x. So now here is the differentiation. Okay, so now we want to use the formula for integration by parts. Now remember that here we have limits, so we need to evaluate them. So we have uv, and then the limits, which are pi over 3 and 0 minus, now here as usual we have u times v, basically, sorry, not u times v, du by dx times v dx. Okay, now we have minus ln sec x times, well, let's write this the other way so that we don't confuse if cos x is inside or outside. So cos x times ln sec x, and the limits, minus, so inside we have tan x times minus cos x. First of all, this minus can be taken out, so here is now positive tan x times cos x. And actually this integration is very simple, because you can simplify tan basically this trigonometric product, because tan x is the same as sine x over cos x, and now this cos x cancels out with this cos x, so you simply have the integral of sine x, which obviously integrates to minus cos x, as we said above. Yeah, so you just have minus cos x ln sec x, and the limits, plus, so sine x integrates to minus cos x, and the limits again, and the answer is equal to minus a half ln 2 plus half. So we have 3x minus 1 over 2x plus 1 times x minus 2, and we want to integrate this fraction. So whenever we have some fractions that have lots of algebraic terms, that's normally integration by using partial fractions. And in this case, we start by writing 3x minus 1, 2x plus 1, x minus 2 as a sum of two fractions. So we have 2x plus 1 plus b over x minus 2. Now, once we have found a and b, then that's going to be easy chain rule integration. So now we just multiply the all the equation by this denominator basically. So every term by multiplied by 2x plus 1, x minus 2. So that gives us 3x minus 1, a times x minus 2 plus b times 2x plus 1. Okay, now let x be equal to 2, and then that gives us 5 is equal to, so the first bracket becomes 0, and then the second one is equal to 5b. That means b is equal to 1. And then now we can set x be equal to minus a half, because 2x plus 1 is equal to 0, is x is equal to minus a half. And now this gives us basically minus 5 over 2 is equal to, again, minus 5 over 2 here times a, and then the second bracket is 0, so a is equal to simply 1. Now the entire of the integration is going to be 3x, so it's going to be 1 over 2x plus 1 plus 1 over x minus 2 dx. Okay, so at this point, both of these can be integrated by just using len. So the first term, 1 over 2x plus 1, integrates to len of 2x plus 1. And actually, here there must be a half, because when we differentiate this, we'll have 2 over 2x plus 1. So this half cancels with that. But for this one, we just have len of x minus 2 plus c. And so we want to integrate this fraction, and this is basically integration by partial fractions, since we have a fraction that has lots of algebraic terms, and I think this is very clear that it's partial fractions. Now, in order to write this as partial fractions, we need to remember that partial fractions only work when we have a proper fraction, but this is an improper fraction because the numerator has a higher power than the denominator. So we first need to use long division to find the polynomial part of the, basically the answer to the division, which is going to be the polynomial part plus the basically the partial fraction part of that. So that's what we need to do here. So first of all, you're going to use the long division in this case. So we divide the entire of the numerator by x squared plus x, which is the denominator. So first of all, if we have x, so x times x squared is x cubed plus x, times x is x squared. So we subtract and we get 0 and x squared plus 2. Now at this point, we also can't go further. Well, actually, here we need to continue, because if you have 1, then it becomes basically x squared plus x, and then when we subtract, then we'll get 2 minus x, and this is the point that we obviously stop, because now we can't continue any further. So now that we have written this in this form, then that means we are essentially going to have, so the fraction is x cubed plus 2x squared plus 2, and denominator is just x times x plus 1, is basically equivalent to the quotient, or just the answer to the division, which is just the polynomial part of the partial fraction, but I mean the polynomial part of the expression. And then the actual partial fraction is for this part, because here we write down the remainder, and then here is just basically the divisor. So in this case, x times x plus 1. So essentially this number here on the denominator. So we always have the remainder here, and then here is the divisor. Okay, at this point, again, we want to convert the second fraction. So this one, 2 minus x, into a partial fraction. So x times x plus 1. So we can rewrite this in the form a over x plus b over x plus 1. Now the thing is, we obviously need to include everything in a single fraction. So this was just a way just to show you that we want to replace this by a over x plus b over x plus 1, and then this big basically collection of expressions is what we use to find a partial fractions essentially. So now we multiply every single term by the denominator, x times x plus 1, and that gives us x cubed plus 2x squared plus 2. And now on the right hand side, it's x plus 1 times x plus 1 again, plus a times x plus 1 plus b times x. And now it's the substitution part. So if we set x is equal to 0, then we'll have 2 is equal to a, essentially. So that's very easy because we'll have lots of cancellations. And when x is equal to minus 1, then in this case, we get 3 on the left hand side, and on the right hand side, we'll just simply, because this one is going to be 0, so we'll just have minus b. And b is equal to minus 3. Now the integration becomes basically x plus 1 plus 2 over x minus 3 over x plus 1 dx. And it's a very simple integration. So because the first term integrates to x squared over 2, the second term integrates to x. Now here is 2 ln x basically, and then here's minus 3 ln mod x plus 1 plus c. The first thing here is that in order to write x squared over x squared minus 4 as partial fractions, just notice that the height, basically the power of the numerator, is the same as the denominator. So we need to use long division first. And by using the long division, so we'll have x squared divided by x squared minus 4, which we have just 1. So we get x squared minus 4, and we subtract, so we just get 4. So that means we'll have 1 plus 4 over x squared minus 4. So it's always the remainder over the divisor. And this is the part that we can actually use partial fractions basically. So we multiply both sides of this by x squared minus 4. So we get x squared is equal to x squared minus 4. Or we can obviously write this as x minus 2 times x plus 2 plus 4. I mean, not 4, but actually once we write in this form, then this is the same as having, so let me change that basically. Let's say, because I skipped one step. So essentially this can be rewritten as 1 plus a over x minus 2 plus b over x plus 2, like this. Now in terms of multiplication, so we'll have a times x plus 2. So again, we are multiplying everything by just x squared minus 4. So, well, we have this on the left hand side. Yeah, and then we get b times x minus 2. Right, now that we have this, we can just simply set x equal to 2, because that cancels out many of the brackets. So we'll have 4 is equal to 4a. So that means a is equal to 1. And now when x is equal to minus 2, then 4 is equal to minus 4b, which means b is equal to minus 1 now. Okay, so now we can write down the integral as 1 plus 1 over x minus 2 minus 1 over x plus 2, because those are the values of a and b. Now it's just simple log integration, because I mean, using reverse chain rule, which gives us log. So 1 integrates to x, and the second term integrates to ln x minus 2, and the third term integrates to ln minus ln x plus 2 plus c.